Try something really simple with me. Pick up anything, a pen, the phone you're holding, or even your own hand. Look at it. Feel it. You think you know what it's made of, right? Those tiny particles, the ultimate building blocks of matter. Tiny, hard, solid, neat little marbles with diameters somewhere around 10 to 10 meters, sticking together to form everything in your life. You learned that in school, you heard it on TV, and it sounds reasonable. Too reasonable. But pause here for a second. Really explain it to me. What's actually making up the thing you're holding? What are those particles really? Where do they come from? How do they exist? And why do they behave as if they have a life of their own? Most people will say something vague like, well, matter is tiny particles linked together. Yeah, sure, but that's not an explanation. That's just slapping a label on the mystery and hoping I don't ask more. And this is what has puzzled me for years. If the world is made of tiny marbles, why don't they just fall into each other? Why doesn't the electron collapse into the nucleus? Why have atoms stayed stable for 13.8 billion years? If those particles were really mini marbles, then all of us, you and me, the sun, and every atom in the universe would have disintegrated long ago. The truth, and I have to say this, is far weirder than you think. The particle picture we believed in for over 2,300 years, since the time of Democritus around 460 to 370 BCE, is just a convenient myth. It gives us the feeling we understand the world, but it doesn't give us any real answer. It makes the universe look orderly, tidy, predictable, but only if you don't look beneath the surface. Because once you pull that curtain aside, once you look at how nature actually operates, you'll see that the entire particle picture collapses instantly. There are no particles at all, no tiny marbles forming the foundation of the universe. Trust me, I was disappointed too when I discovered this. It shattered the entire intellectual Lego set I had painstakingly built throughout my youth. But in exchange, it revealed a truth more beautiful, deeper, and more honest than anything you've ever heard in your life. So if there are no particles, what are we made of? The answer is both strange and elegant, shattering every intuition you've ever had about reality. Keep holding the object in your hand, just a little longer, and you'll never look at it with the same eyes again. If you want to understand why the particle idea falls apart, we have to go back in time, a bit way back to ancient Greece, where Democritus, around 460 to 370 BCE, proposed a bold idea that many of his contemporaries thought was crazy. Everything is made of the smallest, indivisible pieces, which he called atomos. And that idea, crude as it was, survived more than 2 millennia simply because it sounded reasonable. But then in 1897, J.J. Thomson, a man not particularly fond of reasonableness, dropped a bomb on the whole picture by discovering the electron. See the problem yet? If the electron exists, the atom is no longer indivisible. It can be divided. So Thomson proposed the plum pudding model of the atom electrons, like raisins scattered in a blob of positive charge. A sweet, cute image, and like everything, too cute, wrong. By 1911, Ernest Rutherford fired alpha particles at a thin gold foil, expecting them all to pass through like bullets through paper. But no, about 0.01% of them bounced straight back as if they'd hit a steel wall. Rutherford was so stunned, he said it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you in the face. And from this, he concluded, the atom has a tiny, terrifying nucleus with a diameter of only about 10 meters, so small that if the atom were the size of a stadium, the nucleus would be the size of a fly in the middle of the field. Thus, the planetary model of the atom was born. Electrons orbiting the nucleus like planets around the sun. Beautiful, elegant, and completely unworkable. Because according to Maxwell's theory, any orbiting charge would continuously radiate energy, meaning the electron would lose energy, spiral inward, and crash into the nucleus in about 10 seconds. Let me put it in perspective. If that were true, you, me, Earth, the sun, every atom in the universe would have collapsed before the universe even had time to cool. no stars, no chemistry. No you sitting here reading these words. Just a big bang and nothing. Clearly we were looking at reality the wrong way. And to save the atom from self-destructing, physicists had to do something humans hate: abandon intuition. And then, in an unbelievably short period from 1925 to 1926, a group of young minds like Werner Heisenberg, Erwin Schrödinger, and Max Born unleashed what I always consider the biggest earthquake in scientific thought: quantum mechanics. They said something that made everyone, even the sharpest minds, choke. The electron has no orbit, no path, no neat little circle like you draw in textbooks. All that exists is a wave function specs x, a strange equation that tells you the probability of where the electron might appear, but never where it is in the classical sense. Does that sound absurd? Absolutely. But nature has never cared what you find reasonable. And then in 1927, Heisenberg delivered another blow: the uncertainty principle. You cannot know both the position and momentum of an electron precisely at the same time, not because the measuring instruments are bad, not because technology isn't good enough, but because the electron never possesses both values simultaneously. It isn't a stationary object for you to observe. It is a pattern of behavior, a possibility, a moving cloud of probability. I used to joke with my students: if you think the electron is a tiny ball, forget it right now. The electron is an electron. It's not trying to make your life difficult. It just refuses to live according to your intuition. But even though quantum mechanics saved the atom from collapse, it still carried a classical legacy. It still treated particles as fundamental, and that's when the cracks began to show. Primitive quantum mechanics couldn't describe particles appearing and disappearing, which happens constantly at high energies. It couldn't explain why the vacuum, what we always thought was empty, has irreducible fluctuations. It also couldn't properly describe how forces, especially electromagnetism, work in extreme situations. You can imagine the problem back then was like trying to patch a boat with duct tape while a storm approaches. But then in the 1930s, a quiet but razor-sharp mind, Paul Dirac, appeared. He wrote the Dirac equation, a mathematical work of art combining quantum mechanics with special relativity. And that equation did something no one expected. It demanded the existence of a never-before-seen particle, the positron, the antimatter counterpart of the electron. Dirac didn't want to create the positron. It just showed up as a stubborn mathematical fact. And in 1932, Carl Anderson discovered the positron in cosmic rays. That was a beautiful moment in science when nature smiled and said, "Yeah, you guys got it right." Still, even Dirac didn't go far enough. We were still stuck with the idea that particles are little points in space, but experiments kept saying otherwise. High-energy interactions produced countless new particles. The vacuum looked anything but empty, and calculations became so wild that results often shot straight to infinity. Clearly, we needed an entirely new language. And that's when, in the late 1940s, we Tomonaga in Japan, Schwinger in America, and I, in my messy office at Cornell, came up with quantum electrodynamics, the first mature version of quantum field theory. What we realized was stunningly simple, yet so bold no one had thought of it before. It's not particles sitting in space. Space itself is filled with fields, and what we call particles are just the ways those fields vibrate. Space has an electron field, a photon field, quark field, gluon field, and these fields exist at every point, every moment, throughout the universe. When the electron field vibrates in a certain mode, you get an electron. When the photon field vibrates, you get light. No little marbles moving around, just vibrations, just patterns, just rhythms. If you want a picture, think of a guitar string. The string is still there, not going anywhere. But when you pluck it, you create a vibration mode, and your ear hears the sound, or a bongo drum, my favorite. When you hit the drum head, nothing leaves it. Just ripples of vibration travel across the surface and into the air, or ocean waves. The water doesn't travel from the ocean to the shore. The pattern travels. And in QFT, particles are exactly such patterns, quantum vibrations of fields. QFT doesn't just fix the mistakes of the particle model. It describes interactions with unbelievable precision. It predicts the electron's magnetic moment correctly to 12 decimal places. No theory in human history has achieved that level of accuracy. Once you're comfortable with the idea that particles are no longer the foundation of reality, you start to see the bigger picture. The one quantum field theory forces us to confront. Fields are what fill the universe, and they never turn off. And field here isn't something vague, mystical, or abstractly hard to grasp. A field is simply a quantity that has a value at every point in space. Imagine a temperature field. At every position in a room, you have a different Celsius value, and those values form a field. If you walk from the door to the window, you feel a change. You don't need a temperature particle to explain this. You just need to know temperature is a property present at each point. Quantum fields work in exactly that spirit. The universe isn't a box full of tiny marbles. It's a continuous web of fields. The electron field, quark fields, photon field, gluon field, Higgs field, the entire list of 17 fields in the standard model. They don't sit next to each other like items on a shelf. They overlap, interpenetrate, blend into each other, coexisting completely naturally. There's no safe distance between them. No private zone for this field or that one. Everything is fields, and every point in space contains the full set of those fields. This is what confuses many people when they first encounter QFT. Space is not empty. There's no region of perfect, quiet vacuum, no void where nothing exists. Anywhere you stick your finger between the stars, between atoms, in every seemingly empty gap, the fields are still there. Always. The universe has no off switch. Someone once asked me, if there are no particles, then where is my electron? And I said, you don't have your electron. The entire universe has just one electron field. One. Single. That field stretches across all space, and what you call my electron is just a vibration mode of that same field, appearing in a region you're observing. If you think about it for a moment, this is truly mind-blowing. There's no electron field copy number 1 in your body and electron field copy number 2 in a distant star 50,000 light years away. No local version, no duplicate, just one electron field for the entire universe. If an electron appears in Los Angeles and another in the core of the sun, those aren't two entities. They're just vibrations at two different locations of the same field. I remember the first time I realized this. I burst out laughing, not because it was funny, but because the truth was so audacious. We're used to thinking every object has its own piece. My atoms, my matter, my electrons. But nature doesn't operate on ownership that way. All of us, every person, every whale, every truck, every hydrogen cloud in the Andromeda galaxy are sharing the same set of fields. Nothing is made from separate versions of the laws of physics. No one gets their own personal field package. Every event in the universe happens on the same substrate. This also means the empty space in atoms isn't nothing. Even though most of an atom's volume is the space between electrons and nucleus, that emptiness is still full of fields. The electron field, photon field, quark fields in the nearby nucleus, gluon field holding the quarks together, Higgs field permeating the whole structure, and vacuum fluctuations from all the other fields. The void isn't empty. It's busier than any marketplace you've ever seen. Imagine standing in a concert hall where hundreds of instruments are humming very softly, almost inaudibly, but continuously creating a background of vibrations. That's the vacuum, a universe where every field is active, even if so faintly you think it's quiet. And the most important thing, no field can be removed. You can't take the electron field out of a room or turn the photon field off like a switch. They are aspects of reality. They can't be dismantled, replaced, packaged up and put away. They are the foundation on which everything else is built. So when you touch a table, when light hits your eyes, when a proton forms in the heart of a star, none of it happens because little marbles are colliding. It's because fields are interacting, warping, vibrating, oscillating according to equations so beautiful that if you've ever seen them, you'll understand why we're obsessed with physics. The fields are the stuff of the universe. Once you've gotten used to the idea that fields are what fill the universe, the next step, and also the most important intellectual pivot, is to understand that particles are just the name we give to the stable vibrations of those fields. Nothing more, nothing less. If the field is a guitar string stretched across all of space, then a particle is simply the note that string produces when it vibrates at the right frequency. This idea is so simple it's almost suspicious, but every piece of experimental evidence, every equation, every insanely precise measurement points in exactly one direction. Particles are modes of vibration of the field. You don't need to imagine a little marble flying back and forth. What's really happening is that the field vibrates in a very specific, very stable pattern, and that vibration pattern moves through space like a discrete packet of energy. This is why Einstein had to write his famous equation, E equals h. Thus, a photon cannot have arbitrary energy. It must come in discrete steps, each step corresponding to a particular vibration frequency. The electromagnetic field doesn't vibrate in a soft, continuous way. It vibrates in quantized levels. You can't have half a photon, just as you can't pluck half a note on a guitar string. Either the string vibrates in the right mode, or it doesn't vibrate at all. This is the essence of quantum. Energy appears in packets. Those packets are the particles. Go back to the bongo drum I like to play. When you hit it, the drumhead vibrates in many different patterns. Some patterns produce beautiful, resonant, warm sounds. Those are the stable modes. Some vibrations produce nothing worth hearing. Those are modes that die out very quickly. Quantum fields are the same. Most of their vibrations die out very fast and never become particles. Only certain special modes, those that satisfy the field equations, can propagate without self-destructing. That's why particles are durable. They are the natural vibrations of the field, just like the stable modes of a guitar string. And this is what makes most people new to QFT stop and think. If everything is just vibrations, then why is every electron exactly like every other electron? Why are all electrons in the universe, from the ones in your body to those in the center of a neutron star, 50,000 light years away, absolutely identical, with the same mass of 9.199 times 10 RQ, the same charge of 1 top 622 times 10 mc, the same spin 1, 2. The answer is so beautiful it's almost poetic, because all electrons are identical vibration modes of the same single electron field. There is no type A electron or type B electron. No strong electrons, weak electrons, handsome electrons, or grumpy electrons. No local variants. No defective copies. When the electron field vibrates in exactly that mode, you get an electron. When it vibrates in exactly that same mode at another point in the universe, you get another completely identical electron, identical to the point that you cannot distinguish them even in principle. The field doesn't change the identity of the vibration mode. It just produces the same pattern over and over. If you pluck a guitar string anywhere, the A note at 440 Hz is still the A note at 440 Hz. No worse copy. No worse copy. No knock version. The frequency determines the essence. The electron's charge works the same way. It isn't arbitrary. You can't have an electron with charge 1.5 e or a photon with a little extra charge left over. Those properties don't come from the particle carrying them around. They arise from the structure of the field. The field dictates every characteristic of the vibration mode. That's why every photon is identical. Every electron is identical. Every gluon is identical. You can't create a weird electron. That would be as absurd as saying you want to create a new, special, more personality-filled a note. A note is a note. A mode is a mode. This perfect sameness used to be one of the most beautiful mysteries of classical physics. But QFT explains it in a simple, profound, and inescapable way. The field is the root. Particles are merely manifestations. When you look at matter from this perspective, we've been asking the wrong question all along. We asked, what are particles made of? But the right question is, why does the field vibrate in these particular modes, and only these modes produce stable particles? Or put another way, Why did the universe choose these frequencies, these patterns of vibration, to build everything? When you ask the right question, you see something miraculous. Reality is not constructed from tiny bricks. It is constructed from music, from rhythms, from quanta of energy that appear when the field sings its correct melody. Once you've internalized the idea that particles are just vibration modes of fields, you naturally arrive at one of the strangest and most beautiful aspects of the quantum universe. The vacuum is not empty. It is not nothing. Not a perfectly quiet void. Not a blank backdrop for matter to dance on top of. In reality, the vacuum is like a stage full of vibrations, where fields never stop operating even when no real particles are present. And the reason lies at the very heart of quantum mechanics. Heisenberg's uncertainty principle. This principle says you cannot determine the state of a field, say, its strength and its rate of change, absolutely precisely at the same time. If a field were completely still with zero vibration, it would have an exactly defined energy of one single number. That's forbidden. A field cannot be completely at rest. Space hates silence. Even if you remove every particle, cool everything down near absolute zero, and turn everything off, the fields must still vibrate a little, like an instrument that never stops its background hum. And because the vibration cannot be exactly zero, the vacuum always carries a minimum energy level, 0-point energy. 0-point energy isn't some vague philosophical idea. It's a mandatory consequence of quantum mathematics. Without it, no background vibration, no uncertainty, the entire quantum theory collapses instantly. But you don't have to take my word for it. You can look straight at real experiments measured, repeated, confirmed with the most sophisticated instruments humanity has ever built. One of the strongest pieces of evidence for vacuum fluctuations is the Casimir effect. The idea was proposed in 1948 by Hendrik Casimir. Place two parallel conducting metal plates a few dozen nanometers apart. According to QFT, between the two plates, only vibration modes whose wavelengths fit the distance can exist. Outside the plates, all modes exist. The result: greater pressure from the outside than the inside, and the plates are pulled toward each other. Not because of charge, not because of classical van der Waals forces, but because the vacuum is modified. The background vibrations change, producing a real, measurable force. This is a force that comes from nothing. But now you know the vacuum is never nothing. The first precise measurement of the Casimir effect was done in 1997 with about 15% error. By 2001, research groups improved the techniques and confirmed the effect with accuracy better than 5%. A force originating from vacuum fluctuations measured in the lab is no longer theory, it's physical fact. Another earth-shaking piece of evidence, and one close to my heart, is the Lamb shift. In 1947, Willis Lamb and Robert Rutherford used microwaves to precisely measure the energy levels of the electron in a hydrogen atom. The measured result deviated from the prediction of primitive quantum mechanics. Why? Because the electron doesn't just feel the Coulomb field from the nucleus. It continuously interacts with the vacuum fluctuations of the electromagnetic field. The vacuum jostles the electron a tiny bit, shifting the energy state up or down by a small amount. That small amount is measured with absurd precision, but it matches. The Lamb shift was one of the first triumphs of QED. Only when you include vacuum fluctuations do you get the experimental numbers right. It's golden evidence. The vacuum is a dynamic medium, something real, not a physicist's fancy complication. And if the vacuum is a dynamic field, the question becomes, what exactly is the vacuum? In QFT, it's not the no-particle state. It is the lowest energy state the field can occupy. But that state is still full of tiny vibrations, unremovable wiggles, like the surface of the sea that is never perfectly flat even on a windless night. Vacuum fluctuations also explain why a particle can briefly create and annihilate an electron-positron pair, as long as those vibrations obey the uncertainty principle over an extremely short time. Nature doesn't violate conservation laws, it just exploits the gray area quantum mechanics allows. When you look at the vacuum this way, you realize something very special. The fields are always alive, always breathing, always vibrating, even when no particles are around. Fields don't exist to serve matter. Instead, matter is just a field vibrating intensely. The vacuum is the quiet version of that same field, the minimal version, but never truly silent. I once joked that space hates silence, but it's not a joke. It's the deep meaning of QFT. Absolute silence is forbidden. Vibration is fundamental. Reality cannot stand still. And if the vacuum is an endless sea of vibrations, that means every particle you've ever seen, from electrons and photons to quarks and gluons, is riding on top of that background vibration. Matter never appears on a static backdrop. It lives in an ocean of activity, change, undulation, like waves on an infinite quantum sea. We don't live in an empty space filled with matter. We live in a universe where the vacuum itself is a dynamic entity, structured, energetic, and influencing every process. When you grasp this, you touch the true heart of QFT. The vacuum is the foundation of every event, not just the emptiness between things. And this is only the beginning, because vacuum vibrations also play roles in interactions, in mass, in the stability of matter, and perhaps even in the expansion of the universe. Virtual particles are one of the most misunderstood concepts in modern physics, and it's ironic that someone who helped popularize Feynman diagrams, have to keep explaining that people are picturing them completely wrong. You've seen the diagrams I drew, straight lines, curved lines, weakly lines intersecting at interaction points. They look like maps of particle trajectories, electrons running from here to there, photons zipping across a corner then vanishing, gluons shooting out like fireworks. And yes, they look that way, but they are not that way. Not a single line in a Feynman diagram describes a real particle traveling that path through space. They are not kinetic pictures. They are not cartoons of the universe. They are mathematical symbols to help us theorists avoid writing expressions so long they could kill a fountain pen in an afternoon. Every line in the diagram is part of a calculation, not a little particle running around. I've said this many times. The lines in the diagram aren't paths that electrons follow. They're mathematics that helps us compute. But people still love imagining them dancing, popping in and out like quantum hormones. Time to set it straight. Virtual particles are not real particles. They do not exist in the same sense that a real electron or real photon exists. They are a mathematical term describing intermediate contributions in the calculation of interaction amplitudes. They do not satisfy the energy-momentum relation of real particles. They have no trajectories. They cannot be directly observed in experiments. You cannot catch a virtual particle. You cannot measure their mass. You can't even pinpoint when they exist. If you try to attach a concrete physical meaning to them, you'll get yourself into trouble. But why do we use the word particle for something that isn't a particle? Because language is the worst thing in physics. The human brain loves pictures, loves things that are hard, clear, easy to imagine. Quantum mathematics hates that. So what do virtual particles really do? They are the way the field interacts with itself in the calculation. When you write the equations for the electromagnetic field or the electron field, you'll see terms that describe temporary disturbances, forms of vibration that cannot exist as real particles, but still contribute to the total amplitude. Virtual particles are just the mathematical bookkeeping for those disturbances, nothing mystical, nothing beyond physics, and absolutely no story of real particle pairs popping in and out like in science fiction. But if virtual particles aren't real, why do we talk about them so much? Because they predict numbers that no other theory has ever achieved. Look at one of physics' most brilliant triumphs, the electron's magnetic moment. QED, with all its virtual particles in the calculation, predicts this value correctly to 12 decimal places, and experiments in 2022 confirmed it within an extremely tiny error. To grasp how insane this is, if you measured the distance from Earth to the Moon with equivalent precision, the error would be less than the width of a single atom. A theory that describes invisible vibrations and gets this level of accuracy must contain a piece of truth. Virtual particles don't exist as real particles, but the calculations that include them reflect the deep structure of the field. If they were wrong, the results would have collapsed long ago. Experiment is merciless. Beyond the magnetic moment, there's the Lamb shift we just discussed. Virtual photons had to be included to match the 1947 experimental numbers. The Casimir effect only appears when you accept that the vacuum is full of vibrations and modes are restricted between the metal plates. Virtual particles are the tool that describes that restriction. They work in the shadows, and you never see them. But without them, quantum field theory would miss a whole series of phenomena measured with precision that other sciences can only dream of. Think of it this way. In music, you can't understand the whole song just by looking at the notes. Virtual particles are the backstage vibrations, the harmonic structures that never get loud enough for your ear to hear. But without them, the music would be completely wrong. Virtual particles are like that. They aren't the lead performers. They are the background hum that never stops. And this is the most important thing to remember. Virtual particles are never particles. They do not exist in space-time the way electrons or photons do, but they are an inseparable part of the mathematics that describes how fields operate. We use the word particle only because there's no better term. If you want an intuitive picture, imagine dropping a stone into a lake. On the surface, you see clear ripples. Those are real particles. Below the surface, there are countless tiny vibrations, gentle swirls, reflected waves, interference all blending together but never prominent enough to call a specific wave. They are the background vibration that the water surface must have for the big waves to exist as they do. Virtual particles are like those background vibrations. They never appear as objects, but they always adjust the behavior of the larger vibrations. We shouldn't mythologize virtual particles. They aren't quantum creatures scurrying around in the vacuum. They are just a part of the field's mathematics. Something necessary for the calculation to work. A structural detail that makes the universe run. Interactions are where everything gets most interesting, because a single vibration in one field is fine, but the universe isn't built from solo notes. The universe is a symphony where fields constantly talk to each other, warp one another, respond, and from that create every phenomenon we call a force. If you only had the electron field vibrating in one corner of the universe, and the photon field vibrating in another with no interaction, you wouldn't have light, no electricity, no atoms, no chemistry, nothing resembling the world you're living in. It's the mutual warping of fields, the exchange of vibrations between them, that creates the vivid reality. You already know an electron is a vibration in the electron field, but when an electron moves, what does it do? It distorts the photon field. It disturbs the electromagnetic field. That distortion spreads like a ripple, and when another electron nearby picks up that ripple, that electron responds. Electromagnetic interaction isn't particles exchanging like tennis balls. It's the way fields readjust themselves when a vibration appears. And because this readjustment propagates at the speed of light, we get the feeling that the electromagnetic force travels from one particle to another. But no, nothing physical is traveling, just fields responding to each other. Imagine the electron field as a gigantic sheet of fabric, and each electron is a spot where the fabric is pulled slightly out of place. The photon field is another sheet layered on top. When you tug the fabric at the electron's position, the photon fabric wrinkles along with it, and that wrinkle propagates. Those wrinkles are photons. This isn't a metaphor. This is a mathematical essence. The electromagnetic field obeys Maxwell's equations in QFT form, and every electron disturbance creates a deformation in the photon field. And the beautiful thing is, you don't need exchanging particles to explain the repulsion between two electrons. You just need to understand that the electron field and photon field continuously influence each other, creating a warped region such that the two electron vibrations prefer to stay farther apart than closer together. That's the Coulomb repulsion, but its quantum version is far more beautiful than what popular books describe. Let's look at a familiar experimental example: electron-electron scattering. When two electrons are fired at each other in an accelerator, you don't see them throwing virtual photons at each other like a ball. What happens is the electron field gets warped due to the presence of both vibrations. The photon field adjusts its shape in response to those warps, and the result is that the electron's trajectories change. The calculation you write may include virtual photons, but the physics beyond the math is the fields are restructuring each other, Compton scattering electron. Scattering a photon is the same. In the classical description, it's like the photon hits the electron and bounces off. But in QFT, the reality is that the vibration frequency of the photon field changes because the electron field responds. The photon vibrates differently. The electron vibrates differently, and the result is energy transferred from one mode to another. You don't need objects to collide, just modes of the fields changing. But this sounds a bit abstract, doesn't it? Let's use a more everyday example. Imagine you're speaking into a microphone. Your voice makes the air vibrate. The microphone picks up that vibration and converts it to an electrical signal. The electrical signal makes the speaker cone vibrate. Then finally, the listener's ear receives the vibration back in the air. No object is transferred from you to the speaker cone. No sound marbles fly across the room. Just a chain of vibrations being transformed, deformed, transmitted. Electromagnetic interaction in QFT works exactly like that. The electron field plays the role of the microphone. The photon field plays the role of the speaker, and the vibrations are the message being transmitted. But the way nature carries out this process is more beautiful, more subtle, and precise enough that we measure changes down to parts per trillion in experiments. In a proton, 3 quarks are confined together by the gluon field, the strong field. But the gluon field doesn't just glue the quarks. It boils with countless tiny vibrations, forming a gluon C and a virtual quark C. Yet remember, no particles are dancing in there, just a field continuously responding, changing, warping. A proton isn't 3 marbles in a bag. It's a storm of strong field in which 3 stable quark vibrations emerge as durable structures. This is why 95% of a proton's mass doesn't come from quark masses, but from the vibration energy of the gluon field and the pressure of the field. When you're comfortable enough with this picture, you'll see something very clear. All forces in nature are just the ways fields respond to each other. There is no force as an entity, no thing pushing or pulling. From electromagnetic, strong, weak, to even gravity, all are stories of fields. They talk through vibrations. They exchange information by warping. Interaction isn't discrete events. It's a continuous, universe-wide, never-ending conversation from the electrons in your body to the electrons in neutron stars, thousands of light years away. And do you know what's the most beautiful thing about all this? All the fields, electron field, photon field, gluon field, are part of the same mathematical framework, the same underlying set of equations. No field is an exception. No field is more special. And therefore the entire universe becomes more understandable when we drop the picture of discrete objects and accept the subtler truth. The universe isn't made of stuff. The universe is made of fields' responses when they are questioned. You exist because fields vibrate in a way that makes you stable. Atoms exist because fields find a stable configuration. Light exists because the photon field allows modes to propagate without dying out. Interaction isn't a mysterious mechanism. It's the conversation of fields. And when you look at the world through this lens, everything becomes strangely clear. Force doesn't exist. Only fields talking. The interaction between fields opens up a vivid picture. But to see the deepest beauty of quantum field theory, we have to talk about one of the most brilliant moments in 20th century physics, the moment when mathematics, almost reluctantly, pointed to the existence of something no one had ever seen, antimatter. The story begins in 1928 when Paul Dirac, a quiet man who was perhaps one of the sharpest minds ever to live, wrote the Dirac equation. His goal was simple: combine quantum mechanics with special relativity to describe the electron properly. But the equation he produced was more complicated than he expected. It had negative solutions, answers that seemed unrelated to the world we see. In classical physics, negative solutions are sometimes something you can ignore because they have no clear physical meaning. But quantum mathematics doesn't let you do that. Dirac was forced to confront the fact that his equation was saying something important. Alongside the electron, there must exist another particle with the same mass but opposite charge. If the electron carries charge E, that negative solution suggested a particle carrying plus E. Dirac tried to interpret this in several ways. His first attempt, calling the negative solutions a sea of electrons, created a strange but mathematically consistent structure, but no one really liked it. Finally, he said outright, if my equation is correct, there must be a particle like the electron, but positively charged. Sounds simple. It wasn't. This was a statement that touched the philosophical foundations of physics. Who would believe in a kind of electron with opposite charge that had never been seen? Yet mathematics insisted it must exist. And as always in the history of science, when mathematics is that insistent, nature answers. In 1932, just 4 years after Dirac's prediction, Carl Anderson used a cloud chamber to study cosmic rays and found a track curving in a magnetic field, a particle bending like an electron, but in the opposite direction. Identical mass to the electron, equal but opposite charge, a positive electron. Dirac was right. The particle was named the positron. I want you to pause for a few seconds and really feel that. A single equation, just a string of mathematical symbols, forced us to acknowledge the existence of an entire new half of the universe. Not because we saw it, not because we wanted it, but because mathematics demanded it. That's the beauty of theoretical physics. Sometimes the universe doesn't just allow us to predict the future, it forces us to expand our imagination. But the story doesn't stop there. As QFT matured, we realized Dirac didn't just predict the positron as a particle, he inadvertently touched something deeper, symmetry. In the language of fields, the electron and positron aren't two different kinds of matter. They are just two different vibration modes of the same electron field. You can think of the electron field as an infinite ocean. An electron is a wave crest, a region rising up a positive vibration. A positron is a wave trough, a region tipping down an opposite phase vibration. If you're a creature living under the sea, looking up at the waves, crests and troughs are both changes in the same water surface. Only when you rise above the sea do you see them as different. Similarly, at the fundamental level, electron and positron aren't two independent entities. They're just two manifestations of the electron field vibrating in opposite mathematical directions, one corresponding to negative charge, one to positive charge. This is why electrons and positrons have the same mass. They aren't coincidentally identical. They are two halves of a basic mathematical symmetry. Convergence of spin, charge, and field. When QFT describes the electron, it automatically produces the positron as part of the structure. There is no electron field without its opposite vibration, no crest without a trough. The positron isn't an exotic byproduct. It's an inevitable part of the field language. This explains phenomena that previous physics could never understand. One example, when a photon has enough energy, minimum 1.22 MeV, it can turn into an electron-positron pair. This once horrified classical physicists. Why would light turn into matter? But in QFT, it's simple. The photon field vibrates so intensely that it excites the electron field to produce a crest and a trough simultaneously. Those two opposite vibrations are the electron and positron, and when they meet, they annihilate the crest and trough, meet, and the sea surface returns to flat. Pair annihilation is just the field returning to its quiet state, nothing mystical. The electron-positron pair is also one of the most beautiful proofs of field unity. Imagine a guitar with many overlapping strings. The first string vibrates to produce an A note. The second string vibrates in a symmetric mode, producing complementary bass and treble notes. You don't say these are two different instruments. You say they are two modes of the same system. The universe is the same. When you look at particles as independent objects, the universe looks messy, redundant, without reason. But when you see them as field vibrations, everything becomes simple, structured, and unbelievably beautiful. This deep symmetry leads to many other predictions in physics. Antineutrinos, antiprotons, antineutrons, all of them appear because the corresponding field has both crest and trough. Antimatter isn't strange. What's strange is matter didn't completely annihilate antimatter in the Big Bang. But that's a story for later. I want you to hold on to the ocean image, because it's one of the best ways to understand the elegance of QFT. Wave crests look like matter. Wave troughs look like antimatter. But it's all just changes in the same water. No need for discrete particles. No need for strange marbles created from nothing. Just a field, always there, always vibrating, always possessing two symmetric directions. The positron isn't a bizarre creation of the universe. It's proof that the universe loves symmetry. Proof that reality is woven from deep structures that mathematics can see before you even observe. Pair production is the natural next step after you understand that the electron and positron are just two kinds of vibrations, crest and trough of the same electron field. Once you accept that, the process of light turning into matter is no longer magic. It becomes an inevitable consequence of fields exchanging energy. Let's start with the most basic condition. A photon with at least 1.22 MeV of energy, exactly the sum of the rest masses of an electron and positron, can produce an electron-positron can produce an electron-positron pair. This number isn't arbitrary. An electron has a mass of 511 keV, and so does a positron. So to create a pair, you need at least double that. This isn't creating something from nothing, as many people imagine. Nothing pops out of emptiness. What's really happening is that the energy of the photon field is transformed into vibrations of the electron field, a crest and a trough. Nature doesn't break laws. It just changes form. Energy is converted into field vibration patterns, not new matter in the classical sense. When you pluck a guitar string hard enough, your mechanical energy doesn't disappear. It turns into the characteristic vibration of the string's stable mode. When a photon has enough energy, it plucks the electron field in exactly the mode that produces two vibrations, an electron and a positron. The whole process is like throwing two notes into the air from a single pluck. And the wonderful thing is, we've seen this process countless times in the lab. In accelerators like CERN, LEP, or Tevashron, when you fire high-energy photons or create photons from electron-positron collisions, you see matter and antimatter appear from light. But remember, they don't appear from nothing. They are created when enough energy is concentrated at one point, and the electron field vibrates in its mode. 100 GeV photon in an accelerator is just an extremely intense vibration of the electromagnetic field. When that vibration interacts with the electron field, it can pump in enough energy to produce dozens of electron-positron pairs. It sounds like magic, but it's really just QFT operating according to its equations. At CERN, people have produced pairs by slamming electrons into a heavy metal target. When the electron slows down, it emits high-energy photons. Those photons then interact near a nearby heavy nucleus, and the electron field receives enough energy to split into two opposite phase vibrations. The nucleus just plays the role of balancing momentum in the process. Many people still ask, but where do the electron-positron come from? And the answer always surprises them. There's no from where. They are the electron field of field that always exists everywhere in the universe. The photon just supplies the energy for the field to vibrate in the mode we call particles. Once again, no hidden discrete particles lurking in the vacuum waiting to pop out. No matter bank to withdraw an electron when needed. Just the field. The field's modes are the particles. No energy. Field in low mode. Enough energy. Field in low mode. Enough energy. Field activates high mode. Use the C image again to clarify. You look at the sea and see a wave crest rising. You ask, where did that crest come from? There's no crest storage anywhere. The water was already there. Wind energy creates the crest. The electron field is like the sea surface. It's always there. The photon is the wind. Electron-positron are crest and trough. When the wind is strong enough, the sea starts to sing. QFT doesn't view matter as something that appears from nothing. Matter is the manifestation of the field when energy makes the field vibrate in the right mode. When photons in accelerators reach hundreds of GeV, they can produce not just electron-positron, but muon-antimuon, quark-antiquark, anything that matches the energy level and symmetry of the corresponding field. This is why accelerators like CERN are the most terrifying microscopes humans have ever built. They don't just look at matter. They make fields vibrate in modes you normally couldn't excite. They show you the universe at the level where it reveals its true nature. And what's particularly fascinating is, as you increase energy higher and higher, the number of particles produced from that energy increases strangely fast. That doesn't mean the universe creates more things. It means fields have countless modes, and the more energy, the more modes you can excite. An accelerator is like playing a piano with great force. Instead of one note, you hit a whole chord. But remember, electrons and positrons aren't just opposite in charge. They are perfect symmetries of each other. When an electron-positron pair collides, they don't explode. They cancel each other's vibrations. Electron is crest, positron is trough. When the two meet, the sea surface returns to flat. But energy doesn't disappear. It's transferred to the photon field, producing real photons. The entire process is conservation of energy in its purest form. And this transformation from photon, electron, /positron, photon is the operating principle behind countless phenomena in the universe, from interactions in stars to reactions in the atmosphere, to data we collect in particle detectors. When you see everything as an energy dance between fields, you stop asking where do particles come from and start asking how does the field vibrate when it receives energy. And asking the right question is the first step to seeing the true beauty of QFT. Pair production isn't some rare process. It happens everywhere. Energy is high enough in gamma rays from supernovae, in cosmic ray collisions with the atmosphere, in the cores of pulsars, in accelerators, and even in the earliest moments of the Big Bang. The universe creates matter by making fields vibrate, and the universe destroys matter by returning fields to quieter modes. The field is the foundation. Modes are the notes. Photons are the conductors supplying energy. Pair production leads us straight to a bigger question. If the electron and positron are just two vibration modes of the electron field, then how many fields does the entire universe, with the hundreds of particle types we've ever heard of, actually get built from? And the answer, fortunately, isn't hundreds nor even dozens, just 17 fundamental fields. An unbelievably small number when you realize that everything, stars, planets, your body, the phone you're holding, is just different modes of these 17 fields. We call this collection the Standard Model, one of the greatest achievements the human mind has ever reached. It is the universe's catalog of instruments, and every particle is merely a melody played on them. First comes the quark group, with 6 types. We call them flavors: up, down, charm, strange, top, bottom. Each has its own charge, mass, and behavior. The two simplest ones, up and down, make protons and neutrons. Every atom you've ever encountered traces back to these two modes of the quark fields. A proton is 2 up quarks and 1 down. A neutron is 1 up and 2 down. But don't let the 3-particle picture fool you. A proton actually contains countless gluon vibrations and virtual quark-antiquark pairs churning inside it. The heaviest in the quark group, the top quark, is so massive that it decays almost instantly faster than light can cross the diameter of an atomic nucleus. Yet whether you're talking about quarks in a proton billions of light years away or quarks in an accelerator in Geneva, they are all modes of the same quark field. That means every proton in the universe is the same because it's built from the same field. Next are the 6 leptons: electron, muon, tau, and their 3 corresponding neutrinos. The electron is familiar. It creates every chemical bond, generates electric current, and produces light inside the LED bulbs you use every day. But its 2 heavier siblings, muon and tau, are much more massive versions that exist for extremely short times before decaying. Neutrinos interact with almost nothing. Trillions upon trillions of neutrinos from the sun are passing through your body every second without you noticing. They collide so rarely that you could build a lead wall. A light year thick and neutrinos would still pass through as if it weren't there. Yet, however strange they are, all 3 neutrino families are different vibrations of the neutrino fields. Similarly, the electron, muon, and tau are vibrations of 3 charged lepton fields. So far, that's 12 fields, 6 quark plus 6 lepton. But for the fields to talk to each other, for electrons to interact, for protons to stay bound in nuclei, for decay processes to happen, the universe needs gauge fields that act as intermediaries in interactions. These are four basic ones: the photon field, the gluon field, and the two weak force fields, with three vibration modes that form Vodaru, Twa, and Z. Let's start with the most familiar, the photon field, the electromagnetic field. A photon isn't a little light marble. It's a note played on this field. When the field vibrates in a stable propagating mode, you get light. When it vibrates in non-propagating modes, you get virtual photons, the mathematical components that describe the electromagnetic force. Everything from radio waves to gamma rays is just different modes of the same field. The gluon field is much stronger. It creates the strong force, the force that holds quarks inside protons and neutrons. A proton isn't three tiny marbles. It's a gluon storm with three quarks as three stable eddies within that vibrating sea. The most interesting thing about gluons is that they carry color and therefore self-interact, something photons don't do. This self-interaction is what confines quarks, ensuring they never appear free. Then come W, Hucker, and Z, three vibration modes of the weak force fields. The weak interaction is responsible for nuclear decay and a crucial part of how the sun works. Without the weak force, atoms wouldn't decay, energy wouldn't be released, and your sun would shut off instantly. These three bosons are so massive that they make the weak force weak. They don't travel far like photons because their large mass causes the vibrations to die out very quickly. That's also why the weak force operates only within nuclear scales. Finally, underlying the entire universe is the Higgs field, a field that decides whether other vibrations have mass or not. When a vibration drags through the Higgs field, it slows down and we say it has mass. When a vibration doesn't interact with the Higgs field like the photon, it races along at the speed of light. The Higgs boson, discovered in 2012 at CERN, isn't the particle that gives mass, as the press often says. It's just a very special vibration mode of the Higgs fielder mode that allowed us to prove the Higgs field exists. When you look at all 17 fields, 6 quarks, 6 lepton, 4 gauge fields, and Higgs, you're looking at the complete toolkit the universe uses to create every observed phenomenon. From lightning bolts to rainbows, from decay reactions in stellar cores to a leaf in the Amazon photosynthesizing sunlight. What's astonishing is the standard model needs nothing more to describe everything we've ever tested except for two very big things: gravity and dark matter. But within the realm of what we know for sure, these 17 fields are the entire story. You might be thinking, just 17 fields and everything emerges? And I'll say, yes, and that's even more beautiful than you imagine. The universe doesn't waste. It uses a small set of rules to create infinite structure. A piece of music written with a few notes, but capable of playing endless melodies. Even melodies we've never imagined. The standard model isn't a list of particles. It's a list of fields, the vibrating foundations from which the world grows. And if these 17 fields are the universe's instruments, then particles are merely fleeting melodies. You exist only because the electron field, quark fields, and gauge fields found a stable configuration they like to maintain. And then the Higgs field gives you mass, so you don't fly off like a photon. When you understand this, you see the universe doesn't need hundreds of components. The universe needs only a small ensemble of instruments, but plays them with unbounded creativity. The standard model is the best description humanity has ever had of that orchestra. Once you've seen the full 17 fundamental fields of the standard model laid out like a cosmic set of instruments, the next question is, how do those fields, those invisible vibrating lattices, arrange themselves to create the familiar matter we know? Your hand, the chair you're sitting on, the stars burning thousands of light years away, all are woven from these fields. But the most important thing, QFT, reveals something classical particle models never quite clarified, is this: matter isn't a collection of particles. Matter is a stable configuration of fields, continuously maintained by their interactions. Let's start with the proton, one of the foundational bricks of the world you're living in. In popular textbooks, the proton is drawn as a cute little ball with 3 dots inside, 2 up quarks and 1 down quark. But that's just the easy to teach picture, not the correct one. In reality, if you look, inside a proton the way QFT describes, you'll see an energy storm. The gluon field boiling, quark-antiquark pairs constantly appearing and disappearing, vibrations compressing, twisting, spreading, then self-annihilating. Amid that chaos, three stable vibrations, two up and one down, are the longest-lived modes, and they give the proton its identity. But the proton's mass, the thing that gives you weight, doesn't come from those three quarks. Not 50%, not 20%. More than 95% comes from the vibration energy of the gluon field from the vibrating sea that QFT describes. That means most of the mass in your body is energy trapped in a strong field configuration, not any solid stuff at all. You're made of gluon field energy, packaged into quark structure according to QCD's equations. That's the strange truth. Einstein would have loved EL_8 squared. Doesn't say mass creates energy, but the reverse. Mass is energy, the energy of fields. Leaving the proton, let's go to the electron. The electron field is a different field permeating the entire universe, and the electron, one of the field's simplest modes, forms the outer shell of atoms. A proton is about 1836 times heavier than an electron, but the electron determines chemical properties. Why? Because the electron field doesn't just sit inside the atom. It shapes the atom. When the electron field vibrates around a proton, it forms probability clouds called orbitals, clouds permitted to exist by quantum mechanics. These orbitals aren't paths. They aren't orbits. They aren't particles circling around. They are bound vibration modes of the electron field, constrained by the proton's charge, the atomic shell. All of chemistry and every chemical reaction in the universe are restructurings of the electron field governed by the photon field. The photon field, the electromagnetic field, decides how the electron field is allowed to vibrate. The interaction between electron and photon fields is chemistry. When an electron jumps from one vibration mode to another, it loses or gains energy in the form of a photon. The light you see when burning a fire, looking at the sky, gazing at a candle, or turning on your phone screen is the photon field vibrating in modes the electron field doesn't keep. And here's the beautiful part. Chemistry, something that seems far removed from particle physics, is really the story of the electron field vibrating and the photon field responding. From ionic bonds to covalent bonds to enzyme reactions in your body, all are electromagnetic interactions belonging to the same single photon field. One field stretching across the entire universe. Every electron in every atom is a note played on the same single instrument. Every photon you've ever seen in your life is a ripple on the same sea of light. And there's extremely strong evidence proving that QFT correctly describes this symphony of fields, the hydrogen spectrum. Since the 1890s, spectroscopists have measured the absorption and emission lines of hydrogen atoms. They found that electrons prefer to jump between very precise energy levels. But only when QED, a part of QFT, emerged did we calculate those levels with horrifying precision. Horrifying in the scientific sense. Modern measurements show the hydrogen spectrum matches QED predictions to 1 part in 10 AQ. That means, if the hydrogen spectrum were as wide as the length of the United States, the discrepancy between experiment and theory would be the thickness of a single human hair. You know what that means. It means the electron field and photon field really move and sing to exactly the rhythm the quantum equations describe. This matches why QFT is considered the most successful theory humans have ever created. Not because it's beautiful, not because it's logical, but because it's correct to the point of confronting experiment head-on and still winning completely. When you look at matter through the language of fields, all the unnecessary layers of abstraction from classical physics melt away. A hydrogen atom, the simplest piece of matter in the universe, isn't a proton and an electron like two marbles orbiting each other. It's a proton field excited in a stable mode, an electron field vibrating around it in a bound mode, and a photon field tuning the system's energy. When you bring many atoms close together, their electron modes interfere, combine, share, and we call that chemical bonding. But in QFT, Bonding is just the electron field finding ways to arrange its vibration mode so the total system energy is lowest. No assembling particles, just fields finding equilibrium positions. And light arises from the differences between those modes. This is why matter has structure. Because fields have modes, and modes have shapes. Look at the periodic table of elements. You don't need to memorize it to see the wonder. Elements repeat in cycles because the electron field only permits certain bound modes to exist. All the chemistry is written in the mathematics of the electron field itself. The properties of carbon, the thing your body is made of, aren't random. They're the consequence of allowed orbitals in the electron field when constrained by proton fields. And all of this happens thanks to just a few fundamental fields. Quark fields make protons and neutrons. Gluon field gives them mass. Electron field makes atomic shells. Proton field governs chemistry. And Higgs field gives every vibration mass so the system doesn't fly apart. So by understanding fields, you understand matter. By understanding modes, you understand particles. And by understanding interactions, you understand chemistry, light, and even life. But it doesn't stop there. The picture gets even deeper when we ask, if fields can create matter, what holds them together? What gives matter stability? And why are some field configurations more durable than others? Everything I've just told you about protons, electrons, photons, quarks, gluons, all those beautiful and subtle vibrations would completely collapse without one fundamental property, mass. Without mass, all matter in the universe would fly apart at the speed of light like untamed photons, unable to bind, unable to form structures, unable to create atoms, molecules, cells, nothing to call you. And this is where one of the most beautiful, bold, and strangest ideas in 20th century physics takes the stage, the Higgs field. In 1964, not just Peter Higgs, but 5 other independent groups of physicists, Broughton Ingold, Higgs, Gronik, Hagen, Kibble, proposed an entirely new mechanism to explain why some fields have mass and others don't. The wonderful thing is, they all arrived at the same conclusion. The universe contains a special field, permeating all of space, called the Higgs field. And particle mass isn't an intrinsic property, but a consequence of how the vibration modes of other fields interact with the Higgs field. Imagine walking through a crowded room. If you're a celebrity, the crowd clings to you, slowing you down. If you're anonymous, you glide through easily. In QFT, the electron gets caught in the Higgs field a lot, so it moves with difficulty and has mass. The photon interacts not at all, so it races at light speed. The W and Z bosons interact extremely strongly, so their masses are huge, making the weak force weak. This is the Broughton-Ingold-Higgs mechanism. The Higgs field acts as a quantum viscous medium, determining how heavy every field vibration feels. I once joked, and now I think it's truer than ever. You're heavy not because you eat too much, but because you interact too much with the Higgs. But the Higgs field is only part of the story. If there's a field, there must be a vibration mode of that field. And so the Higgs field must have a corresponding particle, the Higgs boson. But the Higgs boson is extremely hard to find because it's so heavy, about 125 GeV, roughly the mass of a xenon atom, but squeezed into a point smaller than a proton. It decays almost instantly. For decades, the Higgs boson was the only missing piece in the Standard Model. It was a theoretical prediction hanging in the space of ideas, challenging every physicist, prove I exist. And then, after decades of preparation, thousands of scientists, and the largest accelerator ever built, the Large Hadron Collider, LHC, at CERN did the unthinkable. In 2012, CERN announced they had observed a new particle with a mass of about 125 GeV, exactly as the Higgs boson was predicted. I want you to pause and imagine that an invisible field spanning the entire universe proposed on paper in 1964, confirmed nearly 50 years later by a 38,000-ton underground machine buried dozens of meters below ground. One of those rare moments when humanity takes an abstract idea and probes it until it becomes evidence. The existence of the Higgs boson means the Higgs field is real. It's not a mathematical trick, not a theoretical crutch. It's the physical foundation of mass. But its mechanism is even more beautiful. In QFT, every field has an energy shape, a graph showing where the field's lowest energy lies. For most fields, the minimum is zero, meaning when the field isn't vibrating, it's zero. But the Higgs field is different. Its energy shape is a Mexican hat potential, a donut-shaped valley. That means the field's lowest value isn't at zero, but at some non-zero value. This leads to a shocking conclusion. Even when you do nothing, even in the vacuum, the Higgs field still has a value, called the vacuum expectation value, VEV. It's always there, covering everything, affecting every other field. You can't turn it off. You can't escape it. It's the background condition every field vibration must obey. When the electron field moves through space, it interacts with the Higgs field's BeV, slowing its vibration mode. That slowing is what we call mass. No need for solid matter. No need for mass-carrying particles. No need for intrinsic mechanisms. Just the Higgs field and its interactions with other fields. Photons aren't held back by the Higgs field, so they have no mass. Gluons are affected indirectly through QCD, but still massless because of their different interaction structure. The WANA, WAR, and ZENG are dragged hard by the Higgs field, so they have enormous masses, making the weak force extremely short-ranged. Mass is no longer natural, no longer a property of particles. It becomes an interaction phenomenon, a consequence, a byproduct of the Higgs field. This shatters our classical intuition that mass is a measure of how much stuff is in something. In reality, mass is how we feel resistance to motion inertia, and inertia is the result of fields getting stuck in the Higgs field. You're heavy because your electrons and quarks interact with the Higgs field in a way that slows them down. If the Higgs field were twice as strong, you would be twice as heavy without eating an extra bite. If it were half as strong, you would be half as heavy without exercising a second. And if the Higgs field was zero, you wouldn't exist because nothing could stay put long enough to form structure. Imagine a universe without the Higgs field, electrons flying at light speed, never held near protons, protons and neutrons never forming nuclei, atoms never existing, chemistry never existing, stars never forming, life having no basis to appear. The Higgs field doesn't just create mass, it creates order. It allows other fields to slow enough for the world to have structure and stability. And that's why the Higgs field isn't a minor detail in the standard model, it's the pillar that lets the universe work the way it does. The Higgs field is what allows you to exist so you can ask questions about it. But the story isn't over. As beautiful as the Higgs field is, it raises a whole new set of mysteries. Why is its value exactly what it is? What does it have to do with dark energy? Are there deeper fields beneath the Higgs field? And of course, why did the universe choose this mechanism and not another? Even though the Higgs field helps us understand why matter has mass, and why the world doesn't dissolve into a storm of photons, it also exposes an even harder question. If every force in nature can be described by quantum fields, then what about gravity? Why does gravity, one of the four fundamental forces, stubbornly refuse to play by the rules of quantum field theory? This is one of those questions that has kept generations of physicists awake at night, and I have to be honest in my usual, straightforward way. I've been trying to understand it for 50 years, and I'm still not sure about anything. To see the problem, let's go back to 1915, when Einstein introduced general relativity, the theory of gravity. This isn't just a theory about a force. It's an entirely new view of reality. Gravity isn't a force in the traditional sense. There's no gravitational field pushing or pulling. No force-carrying particle changing your velocity. Instead, space-time itself curves, and matter simply follows the straightest possible path in that curved geometry. Earth orbits the sun not because it's being pulled, but because the space around the sun is bent. So where's the issue? In QFT, all forces are described by fields living on a fixed background of space-time. The fields vibrate, propagate, interact, but the space-time stage they sit on doesn't change. Space in QFT is like a tennis court. It can be wide, it can be flat, but it doesn't bend itself according to how the players run. But in GR, space-time is the player. It doesn't stand still. It reacts. It has its own dynamics. Its geometry changes according to the energy inside it. This is the most severe incompatibility between GR and QFT. QFT needs a fixed background for the fields to vibrate on. GR says the background is never fixed. Imagine trying to describe waves on the ocean surface, but the ocean surface itself is an emotionless backdrop instead. The surface itself ripples, folds, flips, and tumbles in response to those very waves. That's what happens when you try to quantize gravity. And every attempt we've made so far runs into the same trouble: mathematical instabilities. When you try to describe gravity as a quantum field, you end up with a hypothetical particle called the graviton, a massless, spin-2 particle that would mediate gravitational force the way the photon mediates electromagnetism. It sounds reasonable, but when you start calculating, everything quickly blows up into infinities that cannot be cured by renormalization the way they can in QED or QCD. Quantum gravity, in its standard form, flatly refuses to be tamed. The graviton, to this day, has never been observed. Not because we lack ideas, but because every theory leads to uncontrollable infinities at high energies. To fix this, some physicists proposed string theory. Instead of viewing particles as points, we view them as tiny vibrating strings in different modes. In string theory, the graviton emerges naturally as a specific vibration mode. That sounds wonderful. And to some extent, the theory is beautiful, powerful, and has the potential to unify all forces. But from its proposal in the 1970s until now, there has been no experimental evidence confirming string theory. Not a single vibration mode of strings has been seen. Not a single extra spatial dimension has been measured. Not a single testable prediction has been verified. Another direction is loop quantum gravity. This theory tries to quantize space-time directly, describing it with tiny, discrete loops. But despite many interesting mathematical advances, it still hasn't clearly connected to the standard model, and it hasn't produced testable predictions. Then there are other efforts: asymptotic safety, causal sets, emergent space-time. Each idea is beautiful in its own way, but the universe refuses to reveal the answer. No experiment to date has found any deviation between GR's predictions and reality except in places where QFT also can't reach, like singularities inside black holes or the moment of the Big Bang. Taken together, we have a half-beautiful picture. The standard model describes every force except gravity with unimaginable precision, especially QED accurate to 12 decimal places. GR describes gravity beautifully, from planetary orbits to the gravitational waves LIGO detected in 2015. But the two refuse to talk to each other, and we're stuck in the middle. I always appreciate honesty in science, so I have to say this in my usual voice. I've been trying to understand it for 50 years, and I'm still not sure about anything. I don't know whether we need a new theory like string theory, a new way of looking at fields, or even an entirely different mechanism we haven't imagined yet. Perhaps gravity isn't a fundamental force. Perhaps space-time isn't the background, but an emergent product of quantum fields. Perhaps the graviton exists but lies beyond our current measurement capabilities. Or maybe the entire way we think about fields and vibrations needs to be turned upside down. Why do I say this? Because honesty is the most beautiful thing in science. Sometimes we don't know, and that's not failure. That's a reminder that there's a larger, wider, deeper layer of mystery waiting for us to discover. Gravity is the only missing piece that doesn't fit the picture. And when it does fit, the reality we think we understand may change completely. It's hard to believe, but even in our most successful theories like QED, the electromagnetic part of quantum field theory, when you try to calculate a simple quantity like the self-energy of the electron, you get infinity, not a very large number. Not a hard-to-measure value. Absolute infinity, something ordinary mathematics can't handle. The electron, according to the quantum description, isn't just a solitary vibration. It continuously interacts with the photon field surrounding it. It emits virtual photons and reabsorbs them. Virtual photons create virtual electron-positron pairs, All these vibrations pile on top of each other to form what's called self-energy. When you try to calculate self-energy by summing all these quantum effects, you get a series that becomes infinite. The more you calculate, the more it swells, as if mathematics is mocking you. And in the 1930s, this nearly killed QFT. A theory whose results are infinite cannot be a correct physical theory. Yet the universe still works perfectly. Electrons still have finite mass, still form atoms, still behave exactly according to the laws we observe. That means our mathematics had to be fixed, not the universe wrong. The question was how to fix it. That's where one of the greatest intellectual leaps in the history of science appeared, developed almost independently by physicists Julian Schwinger and Shinichiro Tominaga. The result earned them the Nobel Prize in 1965. The technique is called renormalization. It looks like cheating if you view it from the outside. You sweep away the infinity and replace it with a measured quantity. But the truth is far more subtle. Consider that the electron has an observed mass, the mass you measure in experiments. But theory says the electron also has a bare mass, a number not directly observable. When you calculate self-energy, quantum effects shift the bare mass by infinity. What we do is absorb the infinite part into the bare mass and treat the measured mass as the physically meaningful quantity. Simply put, we don't sweep away infinity. We recognize that the quantity we call real mass already includes all contributions from vacuum fluctuations and self-energy. We don't eliminate the infinity, we bundle it into something immeasurable and keep only the verifiable physical quantity. Renormalization redefines quantities like mass and charge in a way that's immune to infinities. As a result, all predictions become finite and accurate again. This isn't a trick. It's redefining what in the theory is observable and what is merely an intermediate parameter with no physical meaning. But the achievement of renormalization goes far beyond expectations. QED didn't just become stable. It became the most precisely predictive theory in the entire history of science. This accuracy isn't a few parts per thousand or million, it's to 12 decimal places. For example, calculating the electron's anomalous magnetic moment with QED matches experiment at 1 part in 10 Moss square. If you measure the distance from New York to Los Angeles with equivalent precision, the error would be about 1/100th the width of a human hair. That's unprecedented accuracy in any branch of science. No biological model, no aerodynamic equation, no gravitational theory we've ever had reaches that level. Only QED, the quantum theory of electromagnetism, has been properly renormalized. Renormalization didn't just save QFT. It turned QFT into a mathematical tool so powerful it's almost frightening. A theory that can predict thousands of experiments over decades with zero deviation cannot be cheating. It must reflect something truly deep in the structure of the universe. And renormalization paved the way for even stronger theories. QCD, the field theory describing the strong force, is also renormalizable. The weak force too. Even the entire standard model is renormalizable. That means, except for gravity, all of particle physics is mathematically stable. So what does renormalization really teach us? That the universe doesn't care how you imagine it works. It cares about how observable quantities change. That a theory that appears contradictory with infinities popping up everywhere can still be correct if you understand how to separate the physical from the mathematical. And that the beauty of physics doesn't always lie in everything being neat. Sometimes it lies in our ability to turn chaos into razor-sharp structure. But renormalization also reveals something else, something deeper. The matter you think is solid is actually not solid at all. Nothing in your life, from your hand to the stone you throw into a lake, from a concrete building to a diamond, truly touches anything in the intuitive sense you have. This isn't philosophy. This is pure quantum physics. And it starts with one of the most important principles in all of quantum mechanics, the Pauli exclusion principle. The Pauli principle says the two fermions cannot share the same quantum state. It sounds simple, but it's the foundation of the structure of matter. Because if electrons cannot pile on top of each other in the same vibration mode of the electron field, then when you try to force two clouds of electrons close together, they refuse by increasing energy, changing configuration, and creating a repulsive force. That's not classical repulsion, not something bumping into something else. It's the field refusing to overlap, like two musical notes that cannot sound in the same mode when squeezed into the same tight space. Pauli exclusion isn't an electron's choice. It's a law. It's the structure of the universe. But exclusion alone isn't enough to explain the feeling of solidity. The rest comes from electron field repulsion, the electromagnetic repulsion between vibration modes of the electron field. Each electron is a negatively charged vibration. When two electrons get close, the electron field warps, and the photon field responds by creating a region of increased energy between them. The system dislikes that configuration. It tries to keep the vibrations apart. The result is a very real repulsive force pushing your hand away from the table surface, even though you see nothing in between. But remember, no particles actually touch. No electron marble bumps into another electron marble. No photon wedges itself in as a cushion. Nothing material stands between you and the table. Just fields, the electron field and photon field warping to avoid overlapping according to QFT's equations. And here's where the story gets interesting. When you place your hand on the table, the feeling of solidity you have isn't because atoms in your hand touch atoms in the table. It's just field repelling field. No hand touching table. No molecule touching molecule. No point of matter touching another point of matter. This is a truth that's really hard to swallow because every intuition you have about the world about collision, solidity, contact is built wrong from macroscopic experience. At the quantum scale, there is simply no contact. No matter how hard you slam your hand down, you've never truly touched anything. Take a very concrete example. Your hand resting on the table surface. At extremely small distances, electrons in your hand and electrons in the table start interacting, not colliding, not bumping, but the electron field configuration of your hand and the table begin invading the space they're not allowed to share. Pauli exclusion immediately forces the vibration modes to change. The photon field responds by creating electromagnetic repulsion. The result, your hand is pushed back by an invisible tiny distance your eyes can't detect. You perceive that as solid. But in reality, it's just field refusing to overlap field, and the distance between your hand and the table surface at the atomic level still has billions of relatively large gaps. The seemingly smooth surfaces of your hand and the table are actually clouds of electron probability, and those clouds never intersect. They approach, and when they start reaching each other's forbidden regions, repulsion appears. But approach never becomes contact. There is no point of contact. No place where two things meet. If you zoomed in on an atom to the size of a stadium, the nucleus would be the size of a small fly, and the electron wouldn't be a marble orbiting, but a hazy cloud tens of meters away from the center. When two atoms touch, you're talking about two probability clouds that simply never allow each other to occupy the same space. This is why diamond is hard. Carbon's electron orbitals are extremely difficult to compress further. This is why steel doesn't pierce your hand. The electron field refuses penetration. This is why you can stand on the floor without falling through. Pauli exclusion and electron field repulsion hold you up. And this is the most mind-blowing truth. In your entire life, you have never touched anything. You've never touched a table, a door, another person, not even truly sat on a chair. You're just hovering above a quantum field lattice, held in place by configurations the fields allow. This may sound alien, even metaphysical, but it's the only thing consistent with every measurement, every experiment, every QFT model, and every observation from atomic scales to larger material phenomena. When you grasp this, you'll see that the solidity of matter isn't a property, it's a quantum illusion. Beautiful, useful, completely valid in everyday life, but still an illusion. What really exists are fields and their vibration modes, and what you call touch is just the field's protection against two quantum configurations trying to occupy the same space. If the feeling of solidity is just a quantum illusion, then what are you really in the quantum field picture? When you strip away the image of your body as a solid block of matter, when you look down to the cellular level, then molecular, then atomic, you realize something strange. There's no thing at the bottom. No foundational brick. No core particle. Just fields stretching across the entire universe, vibrating in stable modes we call particles, and from those creating everything that seems solid. Your body, what you think of as you, is really just a stable vibration pattern in the 17 fields of the Standard Model, a temporary structure of the electron field, quark fields, gluon field, photon field, and a host of other vibrations held together by the rules the universe has set. If you look at a cell, you see a complex biological machine. But look deeper, and molecules are just vibration modes of the electron field bound by protons and neutrons, which are themselves complex modes of quark and gluon fields. Look even deeper, and atoms are just combinations of modes from the electron field and proton fields, governed by the photon field. And at the very bottom, there's nothing but fields, each field filling all of space, never turning off, never leaving you for even a second. Your body isn't an object. It's an organized pattern, a pattern of information maintained by continuous vibrations of process, not a thing. A candle burns, and the flame isn't an object. It's a process of energy flowing through air. You are the same, not exactly like a flame, but physically you are a highly organized process, a dance of fields. This makes the boundary between you and the universe feel a bit unsettling. You think of yourself as a separate entity, an independent unit. But in the quantum field picture, there are no absolute boundaries. The fields don't stop at your skin. Your electron field and the table's electron field are the same field. There's no my field and the chair's field. The entire universe has just one electron field, one photon field, one quark field. When you touch someone, you're not touching them, but you and they are touching the same field. When you breathe, photons from the sun hit your skin, and the universe is exchanging information between fields of which you're just a small part. The feeling of separateness is just an illusion created by the brain, a tool evolved to help us survive. But from a physics perspective, you are a temporary pattern recorded by the universe in its fields. When that pattern changes form, we call it aging. When the pattern stops, we call it death. But the fields don't disappear. They remain, never turning off. You are not a thing. You are not a stuff. You are what the fields are doing right now. It sounds philosophical, but it's completely physical. When the electron field vibrates in a certain pattern, the proton field stabilizes in a certain pattern. The photon field adjusts energy in a certain pattern. You appear, not as a brick, not as a solid object, but as an event extended in time, a process, an extremely complex kind of melody that the 17 fields are playing together. And the most miraculous thing, there is no two moments when you are you in a rigid sense. The hydrogen atoms in your body are constantly replaced. In 6 months, most of the carbon atoms in you have gone into the air or soil. The water molecules in you come from ancient seas, from clouds, from rivers and lakes, from people who lived thousands of years before you. Your body is like water flowing through a waterfall. It looks stable in shape, but all the material inside is constantly changing. You are pattern, not material. And if you are pattern, what maintains you? The fields. It's the interactions between the electron field, quark field, Higgs field, and photon field that create the stable structure you see in the mirror every morning. You don't own those fields. You are just a temporary consequence of their vibrations. Seen this way, your existence isn't a miracle of biology. It's a miracle of physics. People often ask, if we're just fields, then what makes me and you? And I answer, not the fields, but the vibration patterns. Like two different pieces of music played on the same instrument. Same electron field, but arranged in different modes, creating two different stories. And just like music, you are not separate from the instrument. You are the music being played. When you understand this, you no longer see yourself as an object trapped in this body, but as a continuous part of the universe, woven from the same kind of vibrations as everything around you. You are not in the universe. You are one way the universe knows itself. And when you look at yourself that way, you may begin to see the strange but profoundly real beauty of the quantum field picture. You are not separate. You are not solid. You are not fixed. You are motion. You are process. You are vibration. And most importantly, you are what the fields are doing right now. Once you accept that you are just a temporary vibration pattern of fields, another door opens the door to the beauty of reality. Because when you look at the universe through the lens of quantum field theory, you no longer see chaos, randomness, or disconnection. You start to see music. Everything from electrons in your body to light from distant galaxies is just vibration modes of fields, harmonizing according to rules so subtle that sometimes you don't know whether to call them mathematics or art. A proton is a big, lively, complex melody with millions of gluon vibrations interwoven. An electron is a small but steady note, ringing forever in the electron field. A photon is light racing through space like a high note on an instrument that spans the entire universe. An atom is a chord. A molecule is a chord progression. Matter is music, and life, including the thoughts you're having right now, is an orchestra of trillions upon trillions of vibration modes coordinating perfectly. The most beautiful thing is, this complexity doesn't come from a complicated theory. It comes from simplicity. The universe doesn't use hundreds of thousands of different rules. It uses a few basic equations, simple fields with vibration modes that allow it. That's all. Yet from that simplicity, it gives birth to oak trees, storms, butterflies, mountains, the sun, nerve cells, the human brain, and even the questions you're asking about reality itself. I once said, half joking, half serious, if you understand the equations, you'll hear music in them. And I believe that completely. The quantum field equations, if you know how to look, are like sheet music. They don't draw direct pictures. They just tell how the music should sound, how the fields vibrate, how modes appear, how energy moves. From that, the universe plays its own song. You can hear it with your eyes through light spectra. You can hear it with your ears through sound. You can hear it with gravitational wave detectors like LIGO did in 2015 when it recorded the ring of two black holes colliding a deep bass that no instrument on Earth could produce. And you can hear it with your mind when you look at a QFT equation and realize that all particles, all forces, all phenomena in the universe blend together in a mathematical structure so unified it's almost unbelievable. The universe isn't chaotic. It has melody, it has rhythm, it has structure, it has harmony. The surprising thing is, the simplicity of the fields allows the complexity of the world to bloom. Look at the periodic table. Just two types of quark, up and down, plus the electron field and photon field. And you get every atom from hydrogen to uranium. You don't need a new field for each element. You just need different bound modes of the electron field. One simple version. One different configuration. Look at biology, DNA, proteins, enzymes, all just the electron field following stable modes in three-dimensional space to create shapes, with the photon field controlling the bonds. Life doesn't need a special life field. It just needs the basic fields capable of creating stable structures. And look at your consciousness, emotions, memories, thoughts all are patterns. No thought particles, no consciousness particles. Just vibration modes in neural networks, chemical structures, electromagnetic structures, all governed by the basic fields. When you remember something, you're just reactivating an old chord. When you learn something new, you're writing another section into your own symphony. The beauty here isn't mystery. The beauty here is transparency. Everything complex you see can be traced back to a few simple principles. The universe doesn't need an intention. The universe just needs fields, vibrations, equations, and from that, it gives birth to infinite variety. The truth is, if you could look at the world with QFT eyes, you wouldn't see objects, forces, or motion. You'd see fields filling space like an infinite ocean, and every phenomenon just ripples different vibrations. An electron isn't like a particle, it's like a low note, ringing forever in the background music. A photon is a bright note, traveling at light speed. An atom is a small chord, repeating in the structure of matter. A molecule is a melody. A living thing is a complex passage. A galaxy is a symphony. One strange thing more, this symphony never ends. The fields are always vibrating, even in the vacuum. Vacuum fluctuations are the background music that never goes silent. You can't turn off the universe. You can't turn off the music. And the most wonderful thing is, no matter whether you think your life is small or grand, you are part of that music. Not just a listener. You are one of the melodies the universe is playing to itself. When you understand this, you no longer feel separate from the universe. You no longer feel like a tiny object floating in cold space. You see yourself as part of a larger structure, one note in an infinite symphony. And if you listen carefully, you'll hear what I've felt my whole life. The universe is the music of fields. You don't have to believe it. You just have to learn the equations, and you'll hear the music. And that music still has many passages we haven't understood yet. In fact, the part we understand is just a tiny slice, so tiny, it's almost funny compared to the whole. You might think the Standard Model and QFT have explained everything. You might think those beautiful equations have revealed the full face of reality. But then look at this number. 95% of the universe is dark matter and dark energy. Two things we don't know what they are, don't know what they're made of, don't know why they exist. Everything you can see, stars, planets, atoms, you, me, every laboratory ever built is just 5%. If the universe is a symphony, we've only understood the first few notes, while most of the music still lies beyond our hearing. Dark matter, the thing making galaxies rotate faster than expected, doesn't interact with light, doesn't interact with electromagnetic force, isn't protons, isn't electrons, isn't neutrinos, isn't any vibration mode in the 17 fields we know. It must be something beyond the Standard Model. Dark energy is even stranger. It makes the universe expand faster and faster and faster, as if space itself is inflating. It's not ordinary energy, not the Higgs field, not vacuum energy in a simple way. It's something that makes even the most optimistic physicists sigh. And then you remember, gravity still hasn't been unified with QFT. GR works perfectly on large scales. QFT works perfectly on small scales. But when you try to force them into the same picture-near black hole singularities or the Big Bang moment, everything collapses. Equations blow up into infinities. There's no complete theory to connect them. And the most wonderful, also the most humbling thing is, we know that we don't know. The universe isn't a solved problem. It's like an endlessly opening door, and every time we pass through one, we see 10 more waiting ahead. I always say this not to sound philosophical, but because I truly believe it. I would rather have questions that can't be answered than answers that can't be questioned. I'd rather live in a universe full of mysteries, where every discovery opens more unknowns, than in a world where every answer is considered absolute and unquestionable. Humility isn't weakness, it's honesty. When you look at the universe through QFT, you see the beauty of fields, the simplicity at the foundation, the complexity in the outcome. But when you look farther to galactic scales, to the evolution of the universe, to dark energy, dark matter, quantum gravity, you see a region where the light of our knowledge has only just begun to flicker, not because we're stupid, but because the universe is larger than our imagination. The truth doesn't diminish the beauty of what we've understood. It only increases the beauty of what's left to discover. And that spirit, that willingness to accept what we don't know, is the true foundation of science. We're not keepers of truth, we're seekers. If 95% of the universe still lies beyond our understanding, then a natural and unavoidable question is, are the fields we celebrate as the foundation of reality truly the ultimate foundation? Or are they just the first layer in a deeper structure we've only glimpsed? The Standard Model, beautiful as it is, almost artistic, is certainly not the full picture of the universe. It doesn't explain dark matter, doesn't explain dark energy, doesn't incorporate gravity, and doesn't answer why the fundamental constants have the values they do. These imperfections open up a whole new field of ideas, theories, collectively called beyond Standard Model. One of the most famous candidates is supersymmetry, a hypothesized symmetry between fermions and bosons. SUZ says every particle you know has a superpartner. Electron has electron, quark has quark, photon has photino. If SUZ is correct, the quantum world would be more balanced, more stable, and some superpartners could be the components of dark matter. But to date, Big accelerators like the LHC have found no clear trace of Sue's-wire reminder that beautiful ideas don't guarantee truth. Another major direction is string theory, where all fundamental particles aren't vibration modes of point fields, but vibration modes of extremely tiny strings, too small to observe directly. In this picture, electrons, photons, quarks are just different ways strings vibrate, and crucially, gravity emerges naturally as a vibration mode of the string, the graviton. But for string theory to work, the universe doesn't have just 3 spatial dimensions. It may have 10 or 11, with most curled up so small we can't see them. A bold, beautiful idea, and so far no evidence. Experiments haven't detected extra dimensions, haven't found signs of energy leaking into curled dimensions. Another direction is extra dimensions in Randall syndrome or ADD models, where gravity can leak into extra spatial dimensions, explaining why gravity is billions of billions times weaker than electromagnetism. These ideas lead to interesting predictions like micro black holes, or changes in Newton's acceleration at small distances, but so far all silence. There are also completely new approaches. Emergent gravity not fundamental, but arising from quantum statistics, causal set theory, where space isn't continuous but a network of events. Or Penrose's twistor theory, a redefinition of reality through abstract geometry. Each idea is beautiful in its way. Each has reason to exist, but none has received a firm nod from nature yet. And that's precisely why we must be humble. QFT may be the foundation of modern physics, but no one can guarantee it's the ultimate foundation. It works perfectly in the range we've tested, but beyond that extreme energies, large space-time curvature, Planck scales, we don't know what happens. Perhaps fields are just shadows of a deeper structure, like water waves or surface phenomena of underlying molecular interactions. Perhaps there's a deeper layer, a new language of nature we don't yet have tools to hear. And this is where I'll say what I believed. My whole life a simple but sincere reflection. We've only seen the shadow of the big picture, not because we're stupid, but because the big picture is larger than any individual's intellect. The universe has no obligation to be simple enough for humans to fully understand. But that doesn't diminish the beauty of what we've discovered. It only heightens the excitement of what's still ahead. And here, after traveling the entire journey from Democritus's atomic marbles to quantum fields filling the universe, perhaps it's time for you to try something really simple. Look at your hand, not as before, not as a solid block of matter, but with new eyes that have just passed through QFT, the Higgs field, vacuum fluctuations, renormalization, Dirac symmetry, the standard model, and all the subtle vibrations that create reality. When you look at your hand, you no longer see particles. You've seen very clearly there are no particles, only fields, no electrons as marbles. There is the electron field vibrating in stable modes, no potatoes proton. There are quark fields and gluon fields swirling inside. No mass as an object. There is the Higgs field slowing vibrations. No solidity. There is Pauli exclusion and electron field repulsion refusing to overlap. No object, only field configurations. And as I've said, and will say again for clarity, you are not an object. You are an event, a process, a piece of music, a stable vibration pattern in the 17 fundamental fields. The cells that make up your hand are just molecules bound by the electron field. Molecules are just electron field orbitals around protons. Protons are just gluon storms. Gluons are just vibration modes of the strong field. And all of this exists thanks to the always vibrating vacuum background. There is no layer of matter for you to touch. No hard boundary between you and the universe. Your skin doesn't stop the electron field, nor the photon field, gluon field, or Higgs field. The universe doesn't divide into me and not me. The universe has only fields, and you are a temporary part of that symphony of beautiful but fleeting configuration. And if this makes you feel small, understand it the way I always have. It doesn't make you smaller. It makes the universe bigger. The fact that you are just a field vibration doesn't make you less real. It makes you continuous, not separate, not isolated, not enclosed by the hard shell of self. It pulls you into the same story as matter, as light, as stars, and there's vacuum. It reminds you that when you look at your hand, you're looking at vibration modes once forged in ancient stars, once passed through the Big Bang, once merged into the cosmic field flow, and only temporarily taking the shape you. And that's when the final question arises, one that can't be avoided after this entire journey. If you are just a vibration pattern in quantum fields, then what really is you? I won't answer that question for you. I don't think I should. Science isn't here to close questions, but to open more. And in the end, this is a question each person must answer for themselves. Perhaps you'll see yourself as a temporary pattern. Perhaps you'll see yourself as a continuous part of the universe. Perhaps you'll see there is no fixed you at all. Or perhaps you'll see all of these are both true and beautiful. Tell me, I always like good questions. If you enjoyed this journey of discovery, please subscribe to join me in exploring even deeper mysteries of the universe. See you in the next adventure, where the best questions are always the ones yet unanswered.